Folks, welcome to Chapter 2, Lesson 5, Proving Segment Relationships. All right, over here we have postulates that we're already familiar with and we believe are true. What are postulates? Postulates or axioms are self-evident truths, statements that are true that we all just agree upon because they're so obvious. For example, 2.1 through 2 points is exactly one line. Right, if I had a point in space and one point in space is a unique line between the two of them. We agree upon that. Or if I had 3 points space, like 1, 2, and 3, you could figure out where the unique plane would be. Or look at 2.6. If you have two lines that intersect, they intersect at a point. And if you have 2.7, if you have two planes in space, they intersect at a line, right? Do you believe these are true? Yes, you do. At this point, you know them to be true, and they seem self-evidently true because they are. Those are postulates. Well, today we had two new postulates, a postulate 2.8, the ruler postulate, and 2.9, the segment addition postulate. All right, the ruler postulate is really just saying that you can measure something, right? Remember, the ancient Greeks, they didn't measure anything. So your textbook has said, well, maybe we should introduce the fact that we can measure things. That's called the ruler postulate. The points on any line or line segment can be put into one-to-one correspondence with real numbers. So you have a line right here, the very ancient Greek thing to have. Well, look, we can measure it and say say in this case 3 inches, or set it into any one-to-one correspondence with any particular set of numbers. All right, segment 2.9 you need to memorize because you're going to use it throughout this section, this lesson, and in future lessons. It's the segment addition postulate. If A, B, and C are collinear, then point B is between A and C if and only if AB plus BC equals AC. All right, what are we saying? I mean, it should be obvious to you right here. Right? AB plus BC equals AC. Small plus small equals big. This is actually the definition of betweenness, or a point being between 2 points. Right. Can you see that B is a point that is between the points A and C? If I said, is B between A and C, you'd say yes, right? Well, what's the formal definition for that? Well, A, B, and C have to be on the same line. They must be collinear. And AB plus BC must equal what? AC. So this is just the definition of what it means to say a point's between two other points. All right, remember, segment addition postulate. That's what you're going to call it. Small plus small equals big. All right, you recognize these. These are properties of real numbers, addition property of equality. If I have two numbers, A and B, I can add C to both sides. That's the addition property. I have two numbers, A and B, I subtract C from both sides. Subtraction property. A and B, I divide C on both sides. Division property, right? How about this one? If A equals B, B also equals A. That's called the symmetric property. Or A equals A, that's the reflexive property. Or how about if A and B are equal, I can always replace A with B. What's that? We use it all the time. It's the substitution property. Or that last one right there, A times B plus C is equal to AB plus AC. That's the distributive property. Now, notice these all say of equality. Why do you think they say of equality? Because these are all equations with equal signs. There's the same properties for congruence. For example, we have a reflexive property of equality. We have the reflexive property of congruence. The reflexive property of equality was A equals A. Some number equals itself. Okay, fine. The reflexive property of congruence, some line segment AB is going to be congruent to itself. It's like the same as itself. Or the symmetric property of congruence. If AB is congruent to CD, then CD is congruent to AB, or the transitive property of congruence. If AB is congruent to CD and CD to EF, then AB must be congruent to EF. Same properties, but this is for of congruence. So why is this of congruence? Because we're dealing with congruence symbols, that kind of ancient idea of sameness, right? If we deal with equal symbols, which is equal measure, then we're talking about of equality. All right. And then, of course, we still have our definitions. And we've been using these two definitions all the time, the definition of midpoint and the definition of congruence. So let's remind ourselves, what's a good definition of a midpoint? Well, it's very much like betweenness, right? For a point to be the midpoint of 2 points, like in right there, right? Midpoint, halfway between the two. First of all 3 points have to be on the same line. That'd be collinear. But also what? This distance must be the same as that distance. These two distances must be congruent for this guy and this guy to have a midpoint right in the middle. All right, so if AC is a line segment, maybe I can just draw this for you. If AC is a line segment, sorry that it's not very neat. All right, and we're going to claim that B is the midpoint. What do we have to agree upon? We have to agree that A, B, and C are collinear. This was just like we had for betweenness. Of course, we're still going to have this truth that AB plus BC is equal to AC. That was the segment addition postulate, right? But what's the new qualification that makes B actually a midpoint? AB must what? Equal BC. All right, so whenever we want to prove that AB equals BC, we can get that straight from the definition of the midpoint. Okay, what about the definition of congruence? What's the definition there of congruence? What do you think? What might the definition of congruence be? All right, well, remember, congruence is this ancient Greek idea of sameness. We might say AB is congruent to DE. What does that mean? It means the same. They're the same. How would we have done this in ancient Greece? You know, you'd make AB, you'd swing your compass, you'd place that starting point in another line, you'd swing that same measure, and then you could say, hey, these two are the same. To the modern person, we wouldn't say they're the same. We would say they're congruent. What would we say? The modern person would say that the measure of AB equals the measure of DE. That seems so obvious to us. But remember, the ancient Greeks have visions they were measuring. So we need some theorem that allows us to say what we mean by AB is congruent to DE is that the measure of AB is equal to the measure of DE. That's literally the definition of congruence that your book gives. The ancient Greeks didn't define congruence because they used it all the time, but it was a very common concept to them. And for us, we need a definition of it, and here's our definition. Right? So if you want to convert from ancient Greek to modern math, use the definition of congruence. Or likewise, if you want to go back the other direction, you can use the definition of congruence. All right. Let's try one. C is the midpoint of AB. C is the midpoint of AB. And CB is congruent to BD. All right. Prove that x equals 3/7. Flow proof. What's the first thing you do in a flow proof? Every time. Yes, you write the given and you put what's given in the box. So you're given C is the midpoint of AB and CB is congruent to BD. Next step, okay? Just look at this first chunk. C is the midpoint of AB. What can we know if C is the midpoint of AB, what can we know? What can we know? If C is the midpoint of AB, what can we know? We can know that AC equals CB. How? By the definition of midpoint. All right. Now we've got CB is congruent to BD. What can we immediately know from that? That CB has the same measure as BD. And what are we going to put under the box? The definition of congruence. Very good. All right, now you see it, don't you? AC equals CB, CB equals BD. Therefore, what can we say? We can say that AC equals BD. What property was that? AC equals CB, CB equals BD. Therefore, AC equals BD. What property is that? Come on. It's the transitive property of what? Of donkeys? No, of equality, because we're using equal signs. So the transitive property of equality. All right, what's our next step? Well, we know that AC is this measure right here, and we know that BD is this measure right here. So what can we do? Can we do any idea? We could say 7x equals 3 by the substitution property. AC, that measure is 7x. So we just plug in 7x for AC. Okay. Next step, division property. What are you going to divide both sides by? 7. That's right. And you got to show the actual division. Don't do the division yet, just show it. And then you use the substitution property to finish up. X equals 3/7. Notice you end your proof just like you did every other step. You just write your justification, your reason for each step. You don't write end of proof. You don't write proven or any such thing. But of course, you have reached what you were trying to prove. All right, next. C is the midpoint. Oh, what are we doing now? It's the same exact proof. C is the midpoint of AB, and CB is congruent to BD. Prove that X equals 3/7. So what's new? What's new is we're going to do this in what's called a two-column proof. Most proofs are done in this textbook as two-column proofs. What we used to put in the boxes are our statements. What we used to put under the boxes are our reasons. So right out of the box, what's the first thing we're going to do? Given C is the midpoint of AB, CB is congruent to BD. Now, do you remember the next step? If you look at C as the midpoint of AB, what can you get from that? You get that AC equals CB by the definition of midpoint. And look over here, you can now refer to the step you were looking at to get your information. That's cool, right? You can't do that in a flow proof. Okay, now look over here. CB is congruent to BD. What did we say we could always get from that? CB is equal to BD by the definition of congruence. Very good. Again, I can say, hey, I was referring back to step 1. That's where I was looking. Pretty cool, right? Now, AC equals CB, C equals BD. What can we say? We could say that AC equals BD. By what property was that called? Remember? Transitive property of equality. And look over here. I can say steps 2 and 3, meaning I was looking at steps 2 and 3 together and applying the transitive property of equality. Pretty cool how that works, right? It's very precise. It makes it easy for someone who is reading your proof to see where you were thinking. Much better than a flow proof that way. All right, what was the next step? 7x equals 3 by the substitution property of equality. Then we apply the division property to both sides. Make sure you show the division. And then finally, X equals 3/7. And what do we write for that as a reason? Substitution property of equality. How do we know we're done with our proof? Because what we're trying to prove has in fact been proven. All right, how about this one? CE is congruent to FE. ED is congruent to EG. Prove that CD is congruent to FG. Well, that seems to make sense, right? If this is congruent to that, and this is congruent to that, then this should be congruent to that. It feels right. Can we prove it, though? Can we use our logic? Yeah, what's going to be our first step? Givens. Write all the givens. And your reason is that it's given. Next step, what can we always say from this congruence statement? We can use the definition of congruence to say, right, exactly, modern English. CE equals FE, ED equals EG by the definition of congruence. What next? What do we do? Okay, this is the new thing. Remember we talked about the segment addition postulate? A plus B, sorry, AB plus BC equals what? AC. Small plus small equals big. That's segment addition postulate. All right, we're going to use that here. Well, how would you use the segment addition postulate? If you looked up here, how would you possibly use the segment addition postulate? CE plus ED equals what? CD. FE plus EG equals what? FG. That's the segment addition postulate. So let's just give it a shot. We'll do it this one. CE plus ED equals CD. What are we going to do next? Maybe we're going to use substitution. Yes, we are. How about that? Okay. The substitution we did was we looked at steps 2 and 3. Steps 2 and 3. Look at them together. Put all that information together, and you create this. Can you see it? Some people see substitutions very easily. Some take a lot of training to get there. Okay. So if you need the training, then spend the time with it. Oh, let's look over here. How do we get to this? Can you see FE plus EG equals CD? Can you see how you got there? Can you? Okay, stare at step 3. CE plus ED equals CD. Now, over here, CE equals FE. So can I replace CE with FE? Sure, I'm going to replace this CE right here with FE. ED is equal to EG. So can I replace ED with EG? Absolutely. And then CD, I'm just going to leave as itself. Did you see it? I looked at steps 2 and 3, and I combined them in such a way that I got FE equals EG plus, FE plus EG equals CD. Substitution. I'll repeat it back for you in case you didn't catch it. Look over here. All right. We have CE plus ED equals CD, and we know that CE equals FE, so we're going to replace CE with FE. We know that ED equals EG, so we're going to replace ED with EG. CD is just CD. That's the substitution. What are we going to do next? Segment addition of postulate again. You've already used this, right? That CE plus ED equals CD. So what's the only other segment addition postulate you could use? Do you see it? FE plus EG equals FG. Segment addition, small plus small equals big. FE plus EG equals FG. Segment addition postulate. We use that a lot in this lesson and in future lessons. What is next? More substitution. So stare at lines 4 and 5 and see if you can come up with a substitution. Some people see substitutions easily, others have to work harder at it. You see it? You have a theory? It is CD equals FG. How did that happen? Well, look right over here. Okay. FE plus EG equals CD. Got it in your head? FE plus EG equals FG. Great. I see FE plus EG here. I see FE plus EG equals CD. So in place of FE plus EG, I can always put CD. Great. In place of FE plus EG, I'll just slide CD. So CD equals FG. CD equals FG. Did you see it? All right. Now, what am I trying to prove? CD is congruent to FG. CD is congruent to FG. I already know that CD equals FG. So what do I have to do to transfer myself from modern math back to ancient Greek thought? Definition of congruence, right? It goes both ways. Notice the definition of congruence took us from congruence language to equality language, and it also takes us from equality language back to congruence language. All right, try one. Okay, how about I give you some hints? All right, you're going to do this 2-column proof. You're going to write it all out. Okay? You're not just filling the blanks. You're going to write it all out. All right, you're going to pause this video. You're going to take the time to write the whole thing out. It's probably going to take you, at this point, if it's brand new to you, it could take you 10 minutes. Okay, if you're really good at these, maybe 5, because it's just new. Let's see. Before you do that, though, let's just see. What we're given is that JL is congruent to KM. We're told to prove that JK is congruent to LM. I mean, that seems right to us, right? If this guy's congruent to this guy, and they share the center area, then it's probably true that this guy is congruent to that guy. Okay, pause it, give it a shot. All right, back. Let's find out how you did. Here we go. How'd you do? Okay, this says JL plus K with a line over. I don't know why it's not showing. JL as congruent to KM. That's our given. No problem. Now, what can we always do with these congruency statements? Make them equality statements using the definition of congruence. All right. Now we're going to use this new, very important postulate, segment addition postulate. Look, JK plus KL equals JL. KL plus LM equals KM. That's what we got right here. Then, after segment addition postulate, you're often going to use substitution property. Substitution property of equality. It's right here. JK plus KL equals KL plus LM. Some people see substitution easily. Some have to work at it. What do you think? Can you see it? Can you look at steps 2 and 3 and C4. Ponder it for a second, would you? You see it? Okay, let me explain it to you. Look at line 2, JL equals KM. Now look at line 4, JK plus KL equals KL plus LM. Somehow we're going from 2 to 4. How do we do that? How do we go from 2 to 4? How do we go from JL? How do we go from JL on the left here to JK plus KL? Right here, JK plus KL equals JL. So in place of JL, you can put JK plus KL. How do I go from KM to KL plus LM? Right here, KL plus LM equals KM. So in place of KM, I just put KL plus LM. Can you see it now? All right, now we're going to subtract KL from each side. Properties, that's a subtraction property of equality. If I have something equals something, I can subtract the same number from both sides. And then once I've done that subtraction, the KLs cancel here, the KLs cancel here. I'm left with JK equals LM by substitution property. And then how do I convert back to ancient Greek? Definition of congruence. And I've proven what I need to prove. Fantastic. All right, how about this one? Given AB is congruent to CD, AB is congruent to CD, and CD is congruent to EF, CD is congruent to EF, prove that AB is congruent to EF. That seems right to you, right? This is congruent to that, this is congruent to that, and this must be congruent to that. Seems pretty clear. And that's why it's so short. It's a two-line proof here. All right, what are you going to put in first? That's right, the givens. And then the only question is, how do you get to what you're trying to prove? Well, if AB is congruent to CD and CD is congruent to EF, what can you say? AB is congruent to EF by what property? By the transitive property of what? Donkeys? Of congruence. We already know congruence symbols. So it's the transitive property of congruence. Do you see it? Super easy. This is a demonstration of the transitive property of congruence. Now, when you do proofs, oftentimes you'll be told you can't use something. And the reason is, if you just start with axioms and you want to get to something way down the list of theorems, there's going to be like tons and tons of paths to get you down there. So you have to get skilled in moving through many different paths. So sometimes, in order to teach you a skill, a teacher will say, don't use this theorem. and still try to get to the answer. And this is to build up your skill set. Let's try the same exact problem, but notice here use the transitive property of congruence. I'm going to say now, you cannot use the transitive property of congruence in your proof. See, it's the same proof, but now it's going to be 4 lines because you can't go directly there through the transitive property of congruence. You can use the transitive property of equality, but not of congruence. All right, please pause it, give it a shot, come back, see if you're able to do it. All right, we're back. Let's go through it. Well, we have our givens, no problem. From here, we can immediately transfer to modern math using the definition of congruence. Okay. And then what can we do? AB equals CD, CD equals EF. Therefore, what? AB equals EF. What property is that? Transitive property. Transitive property of what? Dolphins? No, of equality, because we have equal signs now, yeah? That's okay. We said we cannot use the transitive property of congruence, but we can use the transitive property of equality. No problem. All right, what's our last step? We're trying to prove that AB is congruent to EF. We have AB equals EF. That's right. The definition of congruence, which allows us to convert from ancient to modern math and back and vice versa. Okay. This is your homework. Standard, you got 8 problems. Honors, you got 12. I will tell you, this is not going to be easy for you. If you were a year before, born before the year 1600 and you were an educated person and you went like all the way through high school or college or whatever the equivalent was in education, you would do proofs handily in your sleep, because before 1600, the only math textbook anyone really used was Euclid's Elements. And that book starts with postulates, same postulates you've seen, and use deductive logic to prove everything in geometry. That's what it does. It's a whole book of proofs. Like, how many books is the Euclid's Elements? 13 books. Imagine 13 books of proofs, and that's all you do from childhood until you were fully educated. In the classical understanding, an educated person is someone who has worked through all of Euclid's Elements and done all their proofs. But this is brand new to you, because in our modern society, the only high school course you will ever do proofs in is this class, geometry. It's a hearkening back to Euclid's Elements, the father of geometry. And the next proofs course you will ever take, if you ever take one, will be as a math major in your senior year. That's when you take it. And I can tell you that's kind of the weed out course that often math majors will fail, because we're so unfamiliar in the modern era of doing proofs. Proofs are rigorous, proof requires logic, but man, once you learn how to do it, it's quite rewarding and it's a fun game. So what can I say about how you can do this homework? I strongly suggest that there's an answer key, right, attached here. I suggest you look at the problem, try to see what the problem has been giving you, what is trying to be proved, and then I would look at the answer key and see what the proof was like and how it was done, and try to understand it. And once you think you've understood it, I want you to go back and try the proof without looking. It'll be great practice. It's kind of like, remember in this video we did a flow proof, and then we came back and did the same proof in a 2-column proof, and it seemed so much easier the second time. That's what I'm talking about. I think it's going to be a great way to keep yourself from spending too much time on this homework. And there's no other way to do it other than to just start running proofs and getting the skill set. All right, folks, you can do this.